So nucleophile are the species which can able to attract it towards the positively charged center. So there is a difference in rotation of plane polarized light. Such compounds are known as what? Optical isomerism. So what is a dextrorotatory? Dextrorotatory are the compounds which has a capacity to rotate the plane polarized light in a clockwise direction. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Haloalkanes and Haloarenes. Under this unit, we have discussed about the physical and chemical properties of haloalkanes and haloarenes. And today, let us move on to the next topic of this unit by understanding the substitution, nucleophilic, unimolecular reaction and substitution, nucleophilic, bimolecular reaction. So again, for your examination point of view, these two are very important and it can be asked for 3 marks. Okay. In addition to that, we are also going to discuss about some of the stereochemical aspects of nucleophilic substitution reaction, and we are going to understand in the SN1 mechanism how does the optically active alkyl halide will behave. Similarly, in the SN2 mechanism, in the optically active alkyl halide, how does it behave, that we are going to understand. At the last, we are going to discuss about the order of reactivity of various alkyl halide in SN1 and in the SN2 reaction mechanism. Okay, so here you can see that the SN1 can also be written like SN1 as well as with the SN1. No problem of writing with the SN1 and SN2. So in our last class only, already we have discussed about what is a nucleophile, how does it react with the different reagent or with the different reactant to give a different product. So based on this, we are going to understand the nucleophilic reaction mechanism. Okay, the nucleophilic reactions which has been found to be proceed by 2 different reaction mechanism. The first one is SN1 mechanism or SN2 mechanism. Okay, so it is also known as what? Substitution, nucleophilic, unimolecular mechanism or SN1 mechanism, and the second one is substitution nucleophilic bimolecular reactions or second order reaction you can say, and it is written as SN2 mechanism. So first we will understand what is SN1 or first order reaction mechanism or nucleophilic substitution reaction. Okay, the substitution nucleophilic unimolecular reaction. So already we have understood that what is an nucleophile, right? So nucleophile are the species which can able to attract it towards the positively charged center, right? So here, how does the substitution will be taking place and why it is known as unimolecular, we'll understand now. Okay, so the SN1 reactions are generally carried out in a polar protic solvent such as water, alcohol, acetic acid, etc. And the reactions will be taking place in the 2 step. Okay, so the example for this is the tertiary butyl bromide undergo hydrolysis with aqueous KOH to form tertiary butyl alcohol. This mechanism which is known as what? SN1 mechanism, because it is a substitution nucleophilic unimolecular reaction or first order reaction, and the mechanism will be involved with the 2 steps. Okay, so how does the reactions will taking place? By considering a tertiary butyl bromide, we'll see now. So here we have 2-bromo 2-methyl propane, which is nothing but a tertiary butyl bromide. Tertiary butyl bromide, which will undergo hydrolysis with KOH, which is aqueous, to form tertiary butyl alcohol. These reactions are known as what? A substitution nucleophilic unimolecular reaction. I can rewrite this reaction also as CH3, CH3, CH3Br, which is a tertiary butyl bromide, or you can write T also. Okay, so which is allowed to react with KOH, which is aqueous. So what is the reactions which is formed? You can see that the potassium combines with this OH to form KBr. Potassium combines with Br to form a KBr, and similarly this OH goes and attacks to the, because it is a nucleophile which always attracted towards the positively charged center, right, to form an tertiary butyl alcohol. To form what? Tertiary butyl alcohol. So this is tertiary butyl alcohol. So this is a reactions where tertiary butyl bromide undergo SN1 reaction mechanism with the aqueous KOH to form a tertiary butyl alcohol. So this is a substitution nucleophilic unimolecular reaction. We'll see the reaction mechanism so that we will understand how this tertiary butyl bromide is converted into tertiary butyl alcohol. So in the first step, what will happen? The haloalkanes undergo slow ionization to form a carbocation and to form a halide ion. So what does it happen? So in the first step, this is my tertiary butyl bromide undergo slow ionization to form a carbocation. This is carbocation and this is a halide ion. This is a halide ion. You can see that this is a slowest step, okay, where tertiary butyl bromide which undergoes slowest ionization to form a carbocation and to form a halide ion. In the second step, what will happen? The nucleophile, that is OH minus, which attacks the tertiary carbocation to form a tertiary butyl alcohol. So here we have a nucleophile, that is OH minus ion, which goes and attacks a tertiary butyl carbocation, okay, to form what? Tertiary butyl alcohol. So in the examinations, you need to write the two-step mechanism along with this a general mechanism to show that SN1 reaction mechanism. So hope you are understood. So in the first step, what will happen? Tertiary butyl bromide undergoes slow ionization to form a carbocation and halide ion. In the second step, our OH minus ion, that is a nucleophile, which goes and attacks to the tertiary carbocation to form a tertiary butyl alcohol. So if you write these two steps, which is properly balanced along with the general equations, if you write, you'll get a 3 marks. So hope you are understood with this SN1 mechanism or substitution nucleophilic first order reaction. Let us see the kinetics of the reaction. While I am telling this, the SN1 reaction mechanism, I am using the word first order. Why the SN1 reaction mechanism, which is also known as first order reaction mechanism? We'll see now. Okay. So in this type of reaction, the rate of the reactions, which is depending only on the concentration of the haloalkanes, and it is independent on the concentration of the nucleophile. Hence, the rate of the reactions can be written as rate is equal to or directly which is proportional to the concentration of alkyl halide. The step 1, we know that it is the slowest step where our tertiary butyl bromide undergoes slowest ionization process to form a carbocation as well as to form a halide ion. We know that if the reactions which is undergoing the slowing step or if it is going very slowly, we say it is rate determining step, right? We say it is rate determining step, and in this step only one reactant molecules are taking part in the reaction. Hence it is known as what? Unimolecular reaction. So that is why we write rate which is equal to the concentration of tertiary butyl bromide, which is nothing but our reactant. Okay, so the order is 1, so that order can be written as 1. This is why I call the SN1 reaction mechanism as first order reaction mechanism, because only one reactants are involved and it is independent upon the concentration of the nucleophile. Hence it is a first order reaction. Now let us see what is substitution nucleophilic, the bimolecular reaction. Okay, let us take an example for this. I'll take the hydrolysis of methyl chloride as an example. When methyl chloride is heated with aqueous KOH, okay, the methyl alcohols will be formed. We know that when we take the methyl chloride, if you heat it with the aqueous KOH, it forms what? Methyl alcohol with the formation of HCl. If you see the reaction mechanism, the mechanism which involves only one step, and when the nucleophile, the OH minus ion, which attacks the carbon and it approaches the carbon atom only from the side which is opposite to that of the chlorine atom to form a new carbon and OH bond. The formation of this carbon and OH bond and the breakage of carbon and chloride bond which takes place simultaneously, and there is a transition state which has been formed in which both the OH and Cl minus ions are partially bonded to the carbon atom, and to the carbon and OH bonds have become very stronger and it weakens the carbon and chloride bond. So we'll see this reaction mechanism by considering what? Methyl chloride. So this is a methyl chloride, that is CH3Cl. Already I have told that in the reaction mechanism where our nucleophile OH has to attack in the opposite position, not from this side. If it is attacking from this side, it will not taking place, reaction will not taking place. That is why this OH minus ion should always attacks in the opposite side of the chloride. Thereby, it forms a transition state. It forms what? Transition state. So that what will happen? The bond between the carbon and with the Cl, which is going to be weakened, whereas the bond between the carbon and OH will become stronger. Once the bond which has become very weaker, which is get separated out in the form of halide ion, and there is a formation of alcohol, and it is named as what? Methyl alcohol. Remember, the reactions which is taking place in only one step. Okay, whereas the SN1 reaction mechanism which is happening in a two-step. First one is a carbocation formation, second step is the attack of nucleophile. Here in the SN2 reaction mechanism, always remember the nucleophile OH minus ion which is directly attacking to the carbon from the opposite side, thereby it forms a transition state. In the transition state, remember, the bond between the carbon and OH will become stronger and stronger. At the same time, the bond between the carbon and Cl will become weaker. So that the chloride ions will get separated out in the form of halide ion and to form a methyl alcohol. Okay. Coming into their reactions, what does it happens? the configuration of carbon atom under the attack of what? Nucleophile will become invert much that in such a way that it will become what? Umbrella shape. Suppose if you take an umbrella, if strong wind which is breezing, what does it happen? The shape of the umbrella will become inverted, right? So you can see that the shape of the umbrella which is also inverted. You can see that the shape of the methyl chloride to the methyl alcohol, it is completely become inverted. Such configurations are also known as what? Inversion of configuration. Finally, the chloride ions will be completely detached to give an end product of methyl alcohol. So, I can show you that reaction once again. Okay. So, we have methyl chloride. Okay. Methyl chloride, and we know that the nucleophile which comes and attacks to the carbon atom, thereby it forms an intermediate complex which is a transition state where this bond will be get broken up to form an alcohol. To form what? Alcohol. This is a methanol or methyl alcohol. Okay, this is a reaction mechanism which is happening. Okay, coming into the kinetics of this SN2 reaction mechanism. So we all know that just now we have understood that SN2 reaction mechanism which is happening at a single step, right? So that the rate determining step which involves a two reactant, that is, so in the first step only we have observed that both the reactant as well as the nucleophile which is involved, right? So that the molecules of the alkyl halides and the nucleophile, therefore the reactions which is known as what? Bimolecular. Why it is known as bimolecular? Because in the rate determining step only, both the reactant as well as the nucleophiles are involved. So that rate of the reactions can also be written as rate which is equal to the concentration of methyl chloride into the concentration of nucleophile. Okay, so that if you count the number of powers, so order will become what? 1 plus 1, which is nothing but a 2. That is why I have used the SN2 reaction mechanism as second order reaction mechanism. So, hope you all understood with this. Next, we have stereochemical aspects of nucleophilic substitution reaction. So, after understanding this, a nucleophilic substitution reaction, we need to understand some of the common terminology which we are using repeatedly. Okay, we'll see one by one. Some basic stereochemical principles and their notations are as follows. First one is optical isomerism. When if you consider two compounds which are having same molecular formula and also the same structural formula, but they differ in rotation of plane polarized light. Differ in rotation of plane polarized light. Such compounds are said to be optical isomerism. So, what is optical isomerism? If you consider any two compounds having same formula and same structural representation, but when you pass to the plane polarized light, the rotations will be different. So, there is a difference in rotation of plane polarized light. Such compounds are known as what? Optical isomerism. Next, we have optical activity. What is this an optical activity then? A property of a substance which makes it capable of rotating the plane polarized light, that is known as what? Optical activity. It is a capacity, we can say that it is a capacity of a substance to rotate the plane polarized light. They are known as optical activity. There are of two types. Now we have understood that the substance will also have a capacity to rotate the plane polarized. So there are of two types. They are known as dextro-rotatory and the one is known as levo-rotatory. What is dextro-rotatory? We'll understand now. If the compounds which rotates a plane polarized light to the right or to the clockwise, then we say it is dextro-rotatory, or you can say it is D compounds, or you can say it is plus compounds. So what is a dextro-rotatory? Dextro-rotatory are the compounds which has a capacity to rotate the plane polarized light in a clockwise direction. Okay, hence such compounds are known as what? Dextro-rotatory, or D compounds or plus compound. When coming into the levo-rotatory, these are the compounds, it has a capacity to rotate the plane polarized light in an anti-clockwise direction. Hence it is known as what? Levo-rotatory, or you can say that it is the L compounds, or you can say it is minus compounds. So what is the optical activity then? Optical activity are nothing but a capacity of a substance to rotate the plane polarized light, and it can rotate in a two-way. One it is in the clockwise direction, other one is anti-clockwise direction. If it is rotating in a clockwise direction, we say it is dextro-rotatory. If it is rotating in an anti-clockwise direction, we say it is levo-rotatory. Okay. Asymmetric carbon or stereo center. What does it mean? A carbon atom with all the four substrate groups are different. You can see that. You can take the example of this compound where generally I have represented the carbon which is having the 4 valency, and to that all the single bond which has been bonded to the 4 different substrate group. Such compounds are known as what? Stereo center, or you can say that asymmetric carbon. Next we have chiral or chirality. What does it mean? An object which are non-superimposable on their mirror images. They are known as what? Chiral or chirality. Okay. Example is 2-butanol. If you take the structure of 2-butanol, you can see that they are non-superimposable mirror images. Okay. Just you can take your hands. Okay. If you take your hands, you can see that the two hands when you are combined, they are superimposable, right? If you take this hands also and if you do like this, it is also superimposable. Suppose if you keep these palms like this one by one, whether it is superimposable? No. They are known as what? Non-superimposable mirror images. Like that, if you take the butanol, that is 2-butanol, okay, they are non-superimposable mirror images. They never impose one another. Okay. Such compounds are known as what? Chiral compounds, or the property which is known as what? Chirality. Coming into the achiral, okay, the objects which are superimposable on their mirror images, they are known as what? Chirality, okay, or achiral. Example, you can take the 2-propanol. So here you can see that this is a structure of 2-propanol and this is also another structure of the 2-propanol. If you see the mirror images, this is exactly the same, right? And they are superimposable. They are just superimposable. Such compounds are known as what? Achiral compounds. Next we have enantiomers. What is an enantiomers? We'll understand now. Okay. Enantiomers are the stereoisomers which are non-superimposable mirror images, and they are only differs with respect to the rotation of plane polarized light. If one of the enantiomers is dextrorotatory, another will have a levorotatory. Then what are the enantiomers? Remember, enantiomers are also stereoisomers and they are non-superimposable. One which is rotating the plane polarized light in a clockwise direction. One which is rotating in a anti-clockwise direction, thereby it exhibiting the dextrorotatory and levorotatory. And enantiomers possess the identical property, namely melting point, boiling point, solubility, as well as with a refractive index. But there are only three outcomes of the reactions with the asymmetrical carbon atom. They are inversion, retention and racimization. We'll understand one by one. First, I'll go with the retention of configuration. During the reaction, if the reactant has the same configuration of the group around the stereogenic carbon atom as that of the product, then it is known as what? Retention of configuration. It is an configurational coloration when a chemical species, the X and carbon ABC, is converted into chemical species of Y, C, ABC involving the same relative configuration. So here you can consider the carbon atom which are having four different what? Substrate group. If it is get attacked by another reactant, okay. Now, what will happen if the Y which is going to attack this carbon atom, then their configurations will be just changed. Such compounds are known as what? Reduction of configuration. Their configuration is retained, but only the reactant or substrate group which has been replaced. Next, we have inversion of configuration. So, already we have understood that why these inversions will be taking place. In a Essento mechanism, just now we have understood that when a strong wind which is breezing, you know what will happen? The umbrella will be inverted, right? So, it will change its shape. That is known as what? Inversion of configuration. During the chemical reaction, if the product is formed that has opposite relative configuration than that of the reactant, then the phenomena which is said to be inversion of configuration. This already we have understood by studying the Essento reaction mechanism, right? Where the reactant will having its own configuration, but after the product, if you see that, their configurations will be entirely different. Such configurations are known as what? Inversion of configurations, and we have compared that with the umbrella also, and that is also known as what? Walden inversion. Next, we have racemic mixtures or racimization. Okay, the mixtures which are containing two enantiomers in equal proportion will have zero optical activity or zero optical notation, as the rotation is due to one isomers will cancel by the rotation of another isomer, and such mixtures are known as what? Racemic mixtures or racimization we can call. So, we know that enantiomers means either it having a plus form or it will having a minus form, that is dextro or levo, right? So, if you take together, we represent this racemic mixtures as plus or minus, okay. The racemic mixtures is represented by the DL or with a plus or minus. Before the name, the plus or minus, you can take the example of butanol. The process of conversion of enantiomers into racemic mixtures, which is also known as what? Racimization. So now, by looking at this example, you can clearly understand how does the inversion, racimization and retentions will be taking place. There are three outcomes of the reactions of a asymmetric carbon atom. Consider the replacement of X by Y in the following reaction. Okay, so you can see that this is my first reactant. So this is C2H5, CH3, H and Y. So this is a carbon atom which is having 4 different substituent group, right? So if you just react with the X, okay, if you just react with the Y, so what will happen? You'll get a product B, and if the product B which has been react with the X, you'll get this product. So both together which is known as what? A plus B. If A is only the compound which is obtained just by replacement of the group of X by what? Y. So I'm talking about what? Compound A. So in a compound A, the compound A is obtained just by replacing the X with the Y. It is an example for retention of configuration. I can rewrite this just by replacing the Y with the X. So how you will write? C2H5, CH3, and this is hydrogen. Instead of X, instead of Y, you will write a X. So this is an example for what? Retention of configuration. Now I'll go with the B now. In the B again you are replacing the X with the Y, and this is known as what? Inversion of configuration. You can see now, I can rewrite this structure as C2H5, and this is H, and this is CH3. Instead of writing the Y, I'll write a X. And this is an example for inversion of configuration. Inversion of configuration. Now if you see that the retention of configuration and to the inversion of configuration, just imagine this is my reactant, and if you see the product after that reaction, it is completely inverted. Hence it is known as what? Inversion of configuration. Coming into the middle one, that is a product B. If you take the 50% of A and 50% of B, okay. If 50% and 50% mixture of the above two which is obtained, then the process of mixing these two is also known as what? Racimization, and the product is optically active in nature. So if you mix the inversion as well as with the retention, okay, you'll get a product of racimization. Racimization, okay. This is how we can understood this by looking at with this exam. Next we have the SN1 mechanism of optically active alkyl halide. Let's see with the SN1 reaction mechanism, okay. So the SN1 reactions which is accompanied by what? Racimization. Actually the carbocations which is formed in the slowest step, being it is a sp2 hybridized and it is planar in structure, the attack of the nucleophile may be accompanied by either from the either sides, resulting in a formation of product, one which is having the same configuration as that of the alkyl halide and other which is having in a opposite configuration. Hence it is an example for what? Racimization. So here I have considered the example of +2-butanol. So this is an example for +2-butanol, where when the nucleophile which is comes and attacks, what does it forms? It forms what? A transition state. So this is a transition state, and thereby it forms a -butanol to all. So this is a dextrorotatory and this is a levorotatory. Okay, so this indicates that racimization also which is taking place in the SN1 reaction mechanism. Next we have in the SN2. In case of optically active alkyl halide, the product which is formed as a result of SN2 reaction mechanism as inverted configuration, and it is accompanied by the reactant. Already we have understood that whatever the reactant you have considered, that is entirely different of the product. So again I have explained this by considering the 2-bromo octane. You can see that it is C6H13 and one more C will be there, 7, 8. So it is octane, a 2-bromo-octane, which is again going to react with the nucleophile. What does it form? It forms an alcohol, okay, along with the release of halide ion. You can see that this is my reactant and this is my product. The reactant, what is the configuration it is having? It is entirely different of the product. So it is the inversion of configuration, or you can imagine the umbrella shape, okay. Coming into the order of reactivity, that is order of reactivity of various alkyl halide in a SN1 and in the SN2 reaction mechanism. In case of alkyl halide, the tertiary alkyl halide undergo SN1 reaction very faster because of the high stability of tertiary carbocation, right? If you consider the methyl halides, reacts more rapidly in SN2 reaction because there is only 3 small hydrogen atom, and tertiary halides are the least reactive because of the bulky group, which hinders the approach of nucleophile. Thus, the order of reactivity will be goes like this: primary halide, secondary halide, and tertiary halide. This is in case of what? SN2 reaction mechanism. Whereas in SN1, tertiary butyl alcohols or tertiary butyl structures are more reactive. So you can understand this by looking at this example, okay. This is a methyl group, this is a methyl halide, you can say, or methyl chloride you can consider. When the nucleophile which comes and attacks, you can see that the hydrogen atoms are smaller in the nature, so that attacks will be more. But if you see that ethyl group, there are 2 C2H5 groups are increased, CH3 groups are increased, right. So this is C2H5 with the X, right. So this C2H5, again in that the CH3 will become bigger. So this again will become bulker, so that attacks will become lesser and lesser. If you compare one more example by considering the isopropyl, so one more CH3 group which has been attached, so it has become very bulkier to attack with the nucleophile. Whereas in the tertiary butyl alcohol, the attack of the nucleophile towards the tertiary carbocations will become very hard because of the bulky groups, okay. Then the order of reactivity of alkyl halide towards the SN1 and SN2 reaction mechanism will be goes in this way. So as we come to know that in the SN2 reaction mechanism, tertiary carbocations are more reactive towards a nucleophile than that of the primary halide. Whereas in the SN1 reaction mechanism, it will be increases from the tertiary to the primary. Okay, so in the SN1 reaction mechanism, remember, it is always useful for the primary halide, whereas in the SN2, it is useful for tertiary halides. So in the next session, we are going to understand more about the elimination reactions. So by this, I will conclude my session. So what are all the things which I covered in this session, especially the SN1 and SN2 reaction mechanism? It is very important for the examination point of view. And the stereochemical aspects, again, it is an examination point of view. It is very important. Have a look on it. We'll meet you with the next session. Till that, take care. Be safe. Thank you.